Welcome to our deep dive into a truly perplexing cosmological quandary. How empty are cosmic voids? We'll be unpacking this mystery by exploring the findings of A.N. Baushiva's insightful research paper, How Empty Are the Voids?
It's a question that often sparks assumptions of absolute emptiness, a desolate vacuum within the vast cosmic tapestry. But the reality, as we'll uncover, is far more nuanced and fascinating.
Indeed. The challenge lies in reconciling those initial perceptions with the knowledge that voids, while lacking in bright, easily observable galaxies, still contain matter. The question then becomes how much matter and in what forms.
Precisely. While bright galaxies are scarce within voids, we must consider the presence of less luminous objects, like dwarf galaxies, as well as the elusive dark matter, both which are significantly harder to detect. Their presence could contribute a substantial amount of, you could say, hidden mass, altering our understanding of just how empty these voids truly are.
So how did we begin to quantify the density of such vast expanses, particularly when dealing with matter that eludes direct observation?
Vasheva's paper tackles this challenge by taking a clever analytical approach. Instead of attempting to directly observe all the matter within a void, which would be a monumental task, the paper focuses on calculating the minimal matter density at the very center of a void.
This minimum density then serves as a baseline, a foundational measure of emptiness against which we can compare further observations and simulations.
Exactly. The model employed in the paper incorporates several crucial factors that influence this central density, including the expansion of the universe itself, the expansion of the void itself, and the outward flow of matter from the void center.
What's particularly intriguing is the finding that the central density of a void is primarily determined by the amplitude of the initial density perturbation that led to the void's formation in the early universe.
Indeed, it's a remarkable connection between the universe's primordial conditions and the large-scale structures we observe billions of years later. Larger initial, you could say, dips in density, those regions that were slightly less dense than average, result in voids that expand more and ultimately possess emptier central regions.
So the size of that initial density fluctuation, that subtle dip in the otherwise homogeneous soup of the early universe, sets the stage for the void's evolution and its eventual degree of emptiness.
However, there's another layer of complexity to consider: the shape of these voids. Our discussion so far has assumed perfectly spherical voids for the sake of simplicity, but we know that real voids are rarely so symmetrical. They're often ellipsoidal, possessing an elongated shape.
This raises the question of whether the central density calculations derived from a spherical model still hold true for these more irregular ellipsoidal voids.
The paper argues, and quite convincingly, that even for ellipsoidal voids, the central density calculation remains surprisingly accurate. This is because voids possess a peculiar characteristic. They tend to spherize over time due to their unique dynamics.
It's a fascinating concept, this natural smoothing process, whereby voids, despite their initial irregularities, gradually evolve towards a more spherical shape.
As they expand, the matter within them flows in a way that gradually evens out the irregularities, leading to a more spherical configuration. This spherization process, combined with the outward flow of matter from the void center, results in a distinct feature known as the density plateau.
This density plateau is a region at the heart of the void where the density becomes relatively constant, contrasting sharply with the steep decline in density we encounter as we move from the denser regions of the universe into the void's outskirts.
The size and emptiness of this central plateau are directly related to the amplitude of that initial density perturbation we discussed earlier. The larger the initial dip, the more the void expands, and the larger and emptier this central plateau becomes.
So we have this remarkable chain of connections. The size of the initial density fluctuation dictates the extent of the void's expansion, which in turn influences the size and emptiness of its central density plateau.
Now, prepare to delve into a truly fascinating connection uncovered by this research. It links the formation of voids, these seemingly empty spaces, to the formation of galaxy clusters, the densest regions of the universe teeming with galaxies.
This association seems paradoxical at first glance. Voids are defined by their lack of galaxies, while clusters are defined by their abundance. How can these seemingly opposite entities be related in their formation?
The key lies in the concept of Gaussianity, a fundamental assumption about the nature of primordial density fluctuations in the early universe. Essentially, it means that if we were to randomly select a region in the very early universe, it had an equal chance of becoming either a void or a cluster, depending on whether its initial density was slightly lower or higher than average.
So, In a sense, the early universe was a cosmic lottery, with regions randomly assigned slightly higher or lower densities, setting the stage for the formation of either clusters or voids.
Precisely. And this statistically equal probability for overdense and underdense regions, this Gaussianity, allows for a brilliant insight.
What is that?
By comparing the observed formation times of galaxy clusters of a given mass to the expected central densities of voids of corresponding size, we can indirectly estimate void densities without needing to directly observe them.
It's a remarkable feat of scientific deduction, utilizing the observable properties of clusters to infer the hidden properties of voids.
And the results of this analysis are nothing short of startling. Analytical calculations based on this connection between voids and clusters suggest that most voids have a central density only about 50% lower than the average universe density.
50%. That's significantly less empty than one might intuit by simply observing the lack of luminous galaxies within these vast spaces.
Indeed. It challenges the prevailing notion of voids being almost entirely devoid of matter. However, there's a twist. This analytical result stands in stark contrast to findings from N-body simulations, which are often used to model the evolution of large-scale structures. These simulations frequently suggest densities 85–90% lower than the average, implying much emptier voids.
So we have a significant discrepancy between the analytical calculations, which indicate a higher density, and the results of N-body simulations, which suggest a much lower density. What could be causing this disagreement?
It raises the intriguing possibility that despite their sophistication, current N-body simulations might be overestimating void emptiness due to inherent limitations in how they model certain aspects of the universe, such as the complex behavior of dark matter or the subtle interplay between gravity and expansion within a void.
Perhaps, as our simulation techniques advance and incorporate more realistic physics, this discrepancy will diminish. But for now, it underscores the inherent challenges in modeling these vast and complex cosmic structures.
It also reminds us that there's still much to learn about the dynamics of voids, their true density, and the forms of matter they harbor.
This leads us back to our original question. If voids aren't as empty as we initially thought, why do they appear so desolate? Where's all this, you could say, missing matter hiding?
That's a question we'll delve deeper into in our next segment. We'll explore the unique dynamics that govern the evolution of structures within a void, and how those dynamics might explain the apparent paradox of voids being both less empty and yet seemingly devoid of the luminous structures we observe in denser regions of the universe. Welcome back to our exploration of cosmic voids,
Where we're delving into the paradoxical nature of these seemingly empty spaces that, as we've discovered, harbor a surprising amount of matter.
Indeed, we've established that voids, though lacking in the bright galaxies that illuminate denser regions of the universe, are not the desolate vacuums we might initially perceive them to be.
This leads us to a compelling question. If voids contain a significant amount of matter, albeit in less luminous and readily detectable forms, why do they appear so barren? Why haven't those substantial reservoirs of matter coalesced into the same grand structures we observe elsewhere in the cosmos?
The answer lies in the unique dynamics that govern the evolution of structures within a void. Picture a void as a region where the very fabric of space-time is stretched, leading to an accelerated expansion rate compared to the surrounding universe. This accelerated expansion, coupled with the open geometry of a void, creates a peculiar environment that profoundly affects the growth of galaxies and other cosmic structures.
It's as though the void's expansion creates a constant outward pull, a counterforce working against the gravitational forces that strive to draw matter together.
Precisely. Imagine a cloud of gas within a void attempting to collapse under its own gravity to form a galaxy. As it collapses, it encounters this persistent outward pull from the expanding void, hindering its ability to condense efficiently.
So it's a cosmic tug-of-war between gravity, the architect of stars and galaxies, and the relentless expansion of the void, which acts to disperse and scatter matter.
And this struggle has profound implications for the types of structures that can form within a void. It's not just about the overall amount of matter present, but also how that matter is distributed and how it's influenced by the void's peculiar dynamics.
So even though voids might harbor significant reservoirs of matter, the conditions within them hinder the efficient formation of large luminous galaxies.
Exactly. The galaxies that do manage to form in these challenging environments are likely to be smaller, fainter, and dominated by older stars that formed before the void's expansion became too dominant. They represent a relic population, a glimpse into an earlier era of galaxy formation.
It's as though voids, due to their suppressed rate of structure formation, preserve a record of the universe's past, a window into a time when galaxies were smaller and less luminous.
And it's not just the formation of stars that's affected. The distribution of matter within a void is itself sculpted by these forces. As the void expands, matter tends to flow along filamentary structures, creating a delicate cosmic web of interconnected streams and tendrils.
So even though voids are defined by their relative lack of matter, they still possess a degree of structure, a web-like network along which matter flows and congregates.
These filaments act as conduits, channels that funnel matter towards denser regions at the edges of the void, further contributing to the void's apparent emptiness at its core. It's a complex interplay between expansion, gravity, and the flow of matter, all conspiring to shape the void's unique environment.
And how does dark matter, that invisible scaffolding upon which galaxies are built, factor into this intricate cosmic dance within a void?
Dark matter, with its elusive nature and gravitational influence, adds another layer of complexity to the void's story. Because it doesn't interact with light, it's not subject to the same radiative processes that can slow down the collapse of ordinary matter.
So dark matter can potentially clump together more easily within a void, even as ordinary matter struggles against the outward pull of the void's expansion.
While dark matter is also affected by the void's expansion, its ability to condense under gravity without the hindrance of radiative processes could lead to the formation of dense dark matter halos within voids. These halos, though invisible to our telescopes, exert a powerful gravitational pull, attracting ordinary matter and potentially seeding the formation of the smaller, fainter galaxies we observe within voids.
It's a fascinating concept, these invisible wells of dark matter lurking within the void's expanse, acting as gravitational anchors that influence the distribution and evolution of ordinary matter.
The interplay between dark matter and ordinary matter within a void is a subject of ongoing research, a puzzle whose solution could unlock further secrets about the void's structure and evolution.
This brings us to another intriguing aspect of void dynamics, the behavior of the Hubble constant within these underdense regions.
As we've discussed previously, the Hubble constant, a measure of the universe's expansion rate, is actually higher within a void than in the surrounding universe. This means that space within a void is expanding at a slightly faster pace than the cosmic average.
This differential in expansion rates must surely have implications for the evolution of structures within a void. Does this accelerated expansion further hinder the formation of galaxies?
It most certainly plays a role. While the exact nature of this interplay is still being explored, it stands to reason that the void's accelerated expansion further suppresses the growth of structures, making it even more challenging for matter to overcome this outward force and coalesce into galaxies.
It's as though the void, by virtue of its faster expansion rate, creates an environment that favors the dispersal of matter rather than its concentration.
And this difference in expansion rates, while subtle, might also offer a pathway to indirectly measuring the density of voids. By precisely measuring the difference in the Hubble constant between the interior and exterior of a void, we could potentially infer the void's density.
It's a tantalizing prospect, using the very fabric of space-time and its varying expansion rates to probe the hidden properties of these enigmatic cosmic voids.
However, these measurements are incredibly challenging, requiring exquisite precision and sophisticated observational techniques. It's a testament to the ingenuity of astronomers and cosmologists who are constantly pushing the boundaries of what's observable and measurable.
This deep dive has certainly illuminated the complex and paradoxical nature of cosmic voids. They are not simply empty spaces, but dynamic, evolving environments, shaped by a delicate interplay of gravity, expansion, and the flow of both visible and dark matter.
And while they might appear barren at first glance, they harbor secrets about the universe's past, its structure, and the fundamental forces that govern its evolution.
But our exploration isn't over yet. In our final segment, we'll shift our focus to the future of void research, exploring the exciting new avenues of inquiry that promise to further unravel the mysteries of these vast and underdense regions of the cosmos. Welcome back to our final segment, exploring the enigmatic realm of cosmic voids,
where we've journeyed from perceptions of desolate emptiness to a deeper understanding of their complex dynamics and hidden significance.
We've uncovered the paradoxical nature of voids, how they can appear barren while harboring substantial amounts of matter, albeit in forms that defy easy detection.
And we've delved into the forces shaping these underdense regions, from the relentless pull of accelerated expansion to the intricate interplay of gravity and the flow of matter, both visible and dark.
Now let's turn our attention to the future. What lies ahead for void research? What new avenues of inquiry promise to further illuminate these enigmatic cosmic expanses?
One promising frontier lies in the realm of advanced simulations. While current N-body simulations have provided invaluable insights, they still face limitations in accurately capturing the intricate physics at play within voids.
Earlier, we discussed the discrepancy between analytical calculations, which suggest a higher density within voids, and the findings of some simulations, which point to much lower densities. Could advancements in simulation technology help resolve this puzzle?
Indeed. Researchers are constantly pushing the boundaries of computational cosmology, developing more sophisticated algorithms and incorporating more realistic physics into their models. These advancements will allow us to simulate voids with unprecedented detail, capturing the subtle interplay between gravity expansion and the behavior of dark matter with greater accuracy.
So we'll be able to create virtual universes that more faithfully represent the conditions within real voids, enabling us to test our theories and refine our understanding of their evolution.
Precisely. These improved simulations will be crucial for addressing key questions about void evolution, such as the formation and distribution of dwarf galaxies, the properties of dark matter halos, and the impact of voids on the surrounding cosmic web.
It's like having a powerful new lens that allows us to zoom in on the intricate details of these vast, underdense regions, revealing their inner workings with greater clarity.
However, simulations alone cannot paint the complete picture. Observational astronomy also has a vital role to play in our quest to comprehend voids.
What observational approaches hold particular promise for unlocking the secrets of these elusive structures?
One avenue involves studying the faint glow of intergalactic gas within voids. Though incredibly diffuse, this gas can be detected through its absorption and emission of light from distant quasars, those brilliant beacons shining from the early universe.
So it's like using the universe's own backlighting to illuminate these otherwise invisible structures, allowing us to probe their composition and distribution.
Exactly. By analyzing the spectral fingerprints of this intergalactic gas, we can glean valuable information about its temperature, density, and composition, providing further clues about the conditions within voids.
And what about the galaxies that do reside within voids? Can they offer insights into their cosmic environment?
Absolutely. Studying the properties of void galaxies, such as their star formation rates, morphologies, and chemical abundances, can shed light on how galaxy evolution is influenced by the unique conditions within a void.
It's like comparing the ecosystems of isolated islands to those on the mainland. The differences can reveal much about the environmental pressures shaping life in those unique settings.
An apt analogy. These comparative studies can help us disentangle the effects of the void environment from other factors that influence galaxy evolution, such as mergers and interactions with neighboring galaxies.
So it's a multifaceted approach requiring the combined power of advanced simulations, cutting-edge observations, and sophisticated theoretical models to piece together the complete picture of cosmic voids.
And as we delve deeper into these enigmatic spaces, we're bound to uncover new and unexpected phenomena, challenging our assumptions and pushing the boundaries of our cosmological knowledge.
This deep dive has certainly expanded my perspective on cosmic voids. They're no longer simply empty spaces to me, but rather dynamic, evolving environments that play a crucial role in shaping the large-scale structure of the universe.
And as our understanding of voids continues to grow, they're likely to become even more central to our understanding of the universe's grand evolutionary narrative.
I'm excited to see what the future holds for void research. I have a feeling these seemingly empty spaces will continue to surprise and amaze us for generations to come.
Indeed. The cosmos is full of wonders, and voids, with their subtle complexities and hidden depths, stand as a testament to the boundless capacity of the universe to challenge our perceptions and inspire our curiosity.
Thank you for joining us on this journey into the heart of cosmic voids. We hope you've gained a deeper appreciation for the intricate beauty and profound significance of these vast, underdense regions.
And until next time, keep exploring the wonders of the cosmos. There's always more to discover.